Okay, hello.
Okay, so I'd like to thank the organizers for not only organizing this conference, but for the trip this morning, which was just absolutely out of the world. I think one of those of you who didn't go, I think it will be something once in a lifetime. In fact, if I get a chance, if I try to finish early, I would like to show a video called Battle at Kruger, which is for the rest of you who didn't go. Good. So, what I'm going to do is to make some remarks, our attempt to understand how holography actually works in the SYK model. This is work done in collaboration with Antal Jiviki and his student Kenta Suzuki and my student Anivi Ghosh. Even though we have written a few papers on the subject, this is really a work in progress and it will be clear towards the end. There are things which we don't understand, and we are just hoping that the things we don't understand will point to something very interesting. So let me begin with a few general remarks. Examples of holography which we know of almost inevitably involve some large N field theories. And we believe that in some way these large N degrees of freedom get converted into additional dimensions, very non-trivial fact. And in most cases we do not really understand how that happens. There are some exceptions, and notable exceptions are the duality of matrix quantum mechanics and two-dimensional string theory. It's a very old subject, perhaps one of the earliest examples of this kind of duality. And a little more recently, vector models, which are much closer to the kind of things I'll be talking about in the SYK model. So, as I said, that the methods we are going to use are very closely tied with another example of holography, which admittedly is it's sort of less interesting in some respects compared to the standard ADS-CFT duality which follows from string theories, but in many other respects probably more interesting because it gives rise to a very rich structure and of how holography really works. And this had got to do with a conjecture by Klebanov and Monocoque back in 2002, where they conjectured that and gave very strong evidence that the conformal three-dimensional ON vector models, the kind of model which you use in a routine way in statistical mechanics to study phase transitions, are in fact dual to higher spin gauge theories which were developed by Vassiliev in one higher dimensional ADS space-time. So soon afterwards, I and Antal made a suggestion which, as I will see, doesn't work in the way we posed it, but let me mention to you the idea anyway, because that's the core idea. Since these are fields in the vector representation, the way to build singlets is very simple, and basically all singlets can be made out of this bilocal object, which is obtained by taking a dot product of the phi's at separate points. So now let us introduce the center of mass and the relative coordinates of these 2 points, and write the relative coordinate in terms of its magnitude and the angles. Then any function of these 2 points can be now rewritten as a spherical harmonic expansion, where the coefficients, where these y's, sorry, something is happening. Oh, okay. This one is which one is the pointer? This one?
The one in the middle.
One in the middle, okay. So the y's are the spherical harmonics in the transverse space, and the coefficients are now sort of technically functions of the center of mass coordinate and the magnitude of the relative coordinate. So our first instinct was to identify this magnitude of the relative coordinate as a kind of a Poincare coordinate in one higher dimensional ADS, The main motivation behind this is very simple. It's basically because this is a scale, and we know that in ADS CFT duality, the Poincare coordinate plays the role of a scale of the field theory. Now, if this was true, however, all the conformal transformations of these 2 points, or equivalently u and v, which are the center of mass and the relative coordinates, should reproduce the killing symmetries of the higher dimensional ADS. This is almost true, and it does work for the dilatations, the translations, and the rotation generators. As you can see, I've written those generators as acting on sigma. Delta is the conformal dimension of this, and they all act like the way the isometries, the corresponding isometries of the ADS would act on fields of the corresponding conformal dimension. In fact, if you look at the rotation generators, you identify a piece of it, which is the rotation in the relative coordinates, and that gets identified with the spin of the field in ADS T+1. However, this simple-minded identification doesn't really work, and which you can see very directly by looking at the special conformal transformations. And so the first line is what you get from the ADS isometries. The second line, something which is very foreign, and in fact mixes up fields of different spins, so therefore this is not the right way of doing things. It does provide you, just by the symmetries, some kind of representations in the ADS, but it is not the standard linear realization of the ADS symmetries. And I'll tell you a little bit maybe how this was fixed. Now I should make a comment that the Vesseliev theory is supposed to be dual to a gauge version of this model, not the model as I just wrote down. And if you want to do it right on arbitrary manifolds, you should introduce a gauge field with the Chern-Simons gauge field. And then of course these bilocal things have become a bit complicated because there will be a Wilson line which joins the bilocals. This may not be the right way of doing things, but on the plane this can be done by considering bilocals at equal time. In fact, for d equal to t, d equal to 3, Robert and Joao and Antal and Jin invented very cleverly a non-local transformation on the fields as a functions of this u and v, of these bilocals, to fields in the light front quantization, which in the light front quantization would be the correct higher spin fields in ADS space. So the end point of the story is that these bilocal fields themselves should not be considered as the conventional usual higher spin fields, but there is a transformation which they invented, and I'll tell you how this actually comes about. There is also some progress in canonical quantization, and it was a little bit uncomfortable that this was done in the light front quantization. And I think Antal will talk a bit about things which are quite related to this entire subject, so I will not delve into this. However, something interesting does happen when I just take d equal to 1, namely I start with some quantum mechanics. So here I have rewritten those, the SL2R transformations, these global conformal transformations, the way they act upon the center of mass, which I call T, and the relative coordinate Z, and this is how it looks. And you can check these are in fact exactly the killing isometries of the Poincare metric as I have written down before. Interestingly, these are killing isometries of a Lorentzian ADS2, and it doesn't matter whether you start with, and of course if you just start with some theory with just one time, there is no notion of that being Lorentzian or Euclidean. I'll come to that point where that could actually come in, but you always end up with a Lorentzian ADS2. Nevertheless, because of this observation was actually quite crucial in the way Kitaev and then Gross and Rosenhaus and then Antal and collaborators actually solved this model, and so I'll proceed a little bit more about how that happens. I'll come back to the question of Euclidean Lorentzian later on. So brief introduction to the SYK model. It's a model of n real fermions. These are indices of the fermions, I1 through IQ. So the Q fermion interaction with couplings which are random. So it's not a conventional quantum mechanical model because there is this additional probabilistic thing of the couplings have to be drawn from a Gaussian distribution with some weight which is given by a scale which I call J. And as you probably all know, and I will not discuss this any further, this model is of interest because it displays quantum chaos and thermalization. For example, as compared to the C=1 model, one never actually found where is the two-dimensional black hole. There is good reason to believe that this one is a conventional ADS2 black hole. It shows the proper Lyapunov behavior of the right OTOC correlators and so on. The problem of having a random coupling rather than having some fixed coupling as in a standard quantum mechanical theory is somehow easier at large n, where Sajdev and Kitaev in fact showed that when n is large, instead of performing a quenched average, and by quenched average I mean you first compute expectation values and then do the averaging, or in other words, you compute the free energy and average the free energy rather than the partition function. It is good enough to do an annealed average. And then if you do an annealed average, you can treat these as just some fields in a path integral, and you can perform the integration over the fields because that's a Gaussian integral. What you get now is an action which I have written out here before, and in this action what you get is an interaction which is not local, it's actually bilocal. As you can see, there are two integrals over time. And I should pause for a moment and mention that I have written this out strictly in Euclidean signature. If you trace it, that if you started with e to the is and trace what happens after you do the integration, you will find the sign of this term gets reversed. One quick way of seeing that there are two times here, both have to be multiplied by an I. And what that does is that at large n, the saddle point of this model is not real anymore. So that could be one of the reasons why this model is always treated in Euclidean signature. Now there was no ON symmetry to begin with, namely with some random couplings. But after integrating over the random couplings, an ON global symmetry has emerged where these I's now appear as the ON indices. And since it's now like, so that's where the connection to vector models actually come. So this becomes a model, though not with a completely local Lagrangian density, but something which has vector fields in the vector representation of ON. So the usual methods of using bilocal fields can be applied, and that's what Antal and the students did. So introduce a bilocal field because chi's are actually fermion. This actually turns out to be antisymmetric under the interchange of T1 and T2, and by methods which have been known since the 1980s, you can make a change of variable in the path integral from your original fields to these bilocal fields, in which you get an action which is given by this. The key term in the action is the term in the box that comes from the Jacobian in the change of variables from the original fermions to the field, to these bilocal field psi. The other terms are just what the original terms in the original action look like when you write it in terms of the bilocals. The equations of motion are the large n Dyson-Schwinger equations, which is why this is in fact the right collective action at large n, and this is what I have written here. Then comes another simplification, another very interesting feature of the model, which actually makes it solvable to a very large extent. J is an energy scale in the problem, and you can see on the left hand side is the time derivative del t, so that comes also with an energy. And by a rescaling of the fields, it's easy to see that when J is larger than all the other energy scales in the problem, then you can ignore this time derivative term. And then the resulting equation, which is just the second term and the third term, that's a saddle point equation which you need to solve to begin with to perform a large N expansion. That equation can be solved. And this is the solution. So as I said, this is the zero temperature solution. I'll come with the finite temperature solution later on. More interestingly, this is the regime which I'll call the strong coupling, which by definition is the IR of the infrared of the theory. In this limit, there is a new symmetry which has emerged. And this new symmetry is an emergent reparametrization symmetry where the time can be taken to be any other function of time. It includes the conformal symmetries of the SL2 or conformal symmetry of time reparametrizations. Okay. So let's proceed by standard methods of large N. So what you need to do is, in order to read out the spectrum of the theory, you need to expand around the saddle point, which is psi naught, by this fluctuation which I call eta. And then as you would do in any field theory, what you would try to expand the fluctuation in a suitable basis. The basis should be such that it diagonalizes the kernel which appears in the quadratic part of the action. And it turns out that the functions which diagonalizes, and this is intimately tied with the SL2 symmetry in the strong coupling limit, are some specific combinations of Bessel functions which I have written down here. The order of these Bessel functions, nu, can be this discrete series or a continuous series, but nu is purely imaginary, and these are of course tied down to the two well-known representations of SL2R, namely the discrete real ones and the one among the imaginary axis. Now, as I said, these appear because of the symmetry as simultaneous eigenfunctions of the kernel for the quadratic fluctuations and the SL2R Casimir. Of course, any Bessel function is an eigenfunction of the SL2R Casimir. The fact that you have to choose this very particular combination of Bessel functions is dictated by the fact that the SL2R generators actually commute with that kernel. I haven't written down what that kernel for the small fluctuations is, but that dictates uniquely what this combination of Bessel functions has to be. So I've written down what are the orthonormality and the completeness relationships for these functions. So once you do that, it's like going to Fourier space in a standard field theory. You end up with the action in mode space. So these are the analogues of these Fourier transforms of the fluctuation fields, these phis, and then there is this function of this order nu which sits in the middle. So the inverse of this kappa tilde nu minus 1 is going to be the mode space propagator. That function is horrible. It's some ratios of gamma functions which I have written down there. And the spectrum is given by taking this equation and setting it to 1, which gives a highly non-trivial transcendental equation for nu. So I'll call the solutions of the transcendental equation mu equal to Pm. It's easy to see that there are always an infinite number of solutions for any value of Q. Q, remember, was the number of fermions which interacted with each other. However, for any Q, there is a special solution whose value is just exactly 3/2. And there is a reason why this is always a solution regardless of Q. The reason is that you started out with a theory which had a full reparametrization invariance, which included conformal symmetry. And the saddle point, of course, spontaneously breaks that symmetry. So therefore, if I expand around a saddle point, I am going to get a zero mode, which is exactly a zero mode in the strong coupling limit. However, I should warn you, this is not really a symmetry of the full theory. It's only a symmetry in the strong coupling limit. So the zero mode cannot be really an exact zero mode. in fact, there will be an effective action for this mode. The effective action will be given by the parameter which actually controls the smallness in the IR limit. This is the famous Schwartzian action which describes the dynamics of this mode. You can now proceed and calculate the bilocal propagator, where you can calculate in any number of ways in the way I have demonstrated. So you get an answer which is quite expected, sum over the modes with some objects. These RPMs are residues at the poles. The poles are the solutions of the equation, the spectral equation kappa tilde nu equal to 1. I should mention there is actually a double pole at 3 halves. What I have done in writing down this formula is to know beforehand that actually in the full theory this is not a double pole. That pole is actually shifted due to finite coupling effects. So I have sort of introduced a little regulator to do that, with the understanding that I have to treat these modes separately.
So all this is still for the strong coupling?
This is all a strong coupling. Now I'll come to finite coupling.
So far you removed that DT term. So
that's right.
So there was no actual. I mean, you still have a differential equation.
It's still a differential equation.
It's just that term was not there.
The differential equation is appeared because of the bilocal. Right. So then, of course, because this is a strong coupling, it's a zero mode, it leads to a divergent contribution to the propagator. But that, of course, cannot be really divergent if you take into account the finite J effects. And this was calculated by Mandelstam and Stanford. What you find is that the position of the pole gets shifted by this amount. Alpha is just some number, omega is the frequency, so by an amount which is proportional to 1 upon j, as you would expect. You use this shift of the pole to recalculate what would happen to that part of the propagator which was formally infinite in the strong coupling limit, and you get an answer which is proportional to j rather than order 1. So this is why it's called the enhanced contribution. At low energies, this is the most important contribution to the total propagator. And this is the quantity which ties you to the fact that the effective collective coordinate action of this almost broken symmetry is in fact the Schwartzian action. Okay, because there are infinite number of solutions of the spectral equation, what you would expect that whatever this theory is, it should represent something which has an infinite number of fields. So it's a tower of fields. In fact, you could try to massage these 4-point functions of the fermions or 2-point functions of the bilocals in terms of sums of 2-point functions of composite operators of the theory. And this is the form of the primary composite operators written down by Todorov, I think many years ago. And from that you can read out what are the dimensions of these primary operators which are there. This is given by this formula, which is Pn plus half. So this Pn is, and now we sort of understand why Pn actually appeared as the order of the Bessel function. This is like standard ADS-CFT, where delta is d upon 2 plus nu, and this d upon 2 is just half here. So that's why it appeared as the order of the Bessel function. Now in standard ADS-CFT, each primary operator of the theory should correspond to a field. So one would expect that there are an infinite number of fields in ADS2. This is happening because even though this object, this bilocal fluctuation, looks like a function of two variables, the center of mass t and the relative variable z, sorry. even though it looks like a function of two variables, and you might be tempted to think that it's a field in two dimensions, it is actually not, because if we rewrite that original action in position space, what you get is a form like this, where the operator which appears between the two fields is something which is horribly non-polynomial in the ADS Laplacian, which I call dB. So it's a term, it's an action with an infinite number of terms of more and more derivatives, and such an object of course cannot represent a standard normal field.
So what was eta?
Eta was the fluctuation around the saddle.
So this is purely you expanding that
You just-
bilateral.
Yeah, so I wrote that in mode space. This is a position space analog of that. Okay.
And T and Z were just center of mass and relative.
Center of mass and relative so far. Now it has been argued that as you see at strong coupling, the dominant contribution to the propagator comes from this almost zero mode, and so somehow it's thought that this is like, so this is like the low energy sector of the theory if you wish, and a natural guess for that is that it represents some dilaton gravity in two dimensions, a theory whose background has a solution which is ADS2, and indeed the favorite model for that is something called Jacques-Taitelbaum gravity, which has the standard gravity action with a dilaton field phi, which is the one which makes it non-trivial even in two dimensions, and there is some matter which we need not worry about at the moment, but which will be the main part of our topic. The classical solutions of that, as I said, are ADS2. In fact, in two dimensions, this model, everything is ADS2. The non-trivial thing is the dilaton. The dilaton is a function of z, which is the ADS2 Poincare coordinate, and there is a parameter a, and the identification leads you to believe that a is proportional to 1 upon j. So that a strong coupling, there is really an exact SL2R isometry of the background. It is broken at finite values of the coupling by the dilaton itself. I'm not using it because I'm messing this up. Okay. This theory also has a black hole solution. Once again, the non-triviality of the black hole solution actually comes from the dilaton. The rest of it is just ADS Rindler, which I have written down up here. And this is supposed to be dual to the SYK model by the standard in the lower of ADS CFT to be dual to the finite temperature version of the SYK model. Okay, so with these ingredients, I should also mention that this kind of thing is not always restricted to Jacques-Taitelbaum. The Schwarzian action is actually quite universal. It appears in many places. In particular, I mean, these people, Mandel, Naak and Warrior showed that it actually appears of Polyakov action in two dimensions. The Schwarzian action itself describes in a way which is understood very well the near horizon geometries of both 3+1 and 2+1 dimensions, which is some recent work by these people. So it's something which universal action of broken SL2R symmetries. So we want to learn. So far, see, I should just stop it. Just going back somewhere. So we want to ask, in what sense is this idea that the arguments of the collective field are somehow related to a dual space-time? We want to make this a little more concrete. So before doing that, let me point out some issues with this. So as I said, the coordinates of the bilocal space do act in t equal to 1 as coordinates of some Poincare patch. However, and in fact, the bilocal propagator is the sum of scalar ADS2 propagators. Those ADS2 propagators are not, of course, the standard propagators. These are propagators with some non-standard boundary conditions at the Poincare horizon. This is because of these Z combinations of the Bessel functions, not the Bessel functions themselves, there is a possibility that one should really consider this space, which I'll call bilocal space, as not ADS2 plus D sitter, because that gives you the leeway of having alpha type vacuum of de Sitter. In fact, to a very large extent, these things can be identified with the modes which appear in the alpha type vacuum. However, and all the things are messed up, but more significantly, all our calculations were done in a Euclidean theory. In fact, as I mentioned, if you did start with the Lorentzian theory, you would end up finding that the saddle point solution is not real. Okay? And things wouldn't work the way it is. And this is the reason also why there is no I in front of the propagator, which usually typically appears in a series in a Lorentzian signature. So it is natural to ask, how could it be that the dual lives in a Lorentzian theory, even if you started out with Euclidean theory? In standard ADS-CFT, this would never happen. So it leads to the conclusion that the bilocal space cannot be itself the dual space-time in the standard sense of ADS-CFT. So this is one of the main issues which I'll address and our ideas about how to solve this problem. But before doing that, let me discuss an intriguing aspect of this model.
So can I ask a bit about
Yes.
the logic here? So in standard ADS-CFT,
Right.
we can start with the Euclidean theory at the boundary. Okay.
Yes,
And we say that the dual will be some
Euclidean
some
theory.
Euclidean geometry that
Yeah.
you can think of this as filling the shell, which is a Euclidean theory.
That's right.
And then that's it. And that's if we were Euclidean people, we would be very happy with that.
Very
That would
happy
be
with
the end of
that.
it.
Right.
And now, if you want to get Lorentzian physics out of that, all you have to do is you have to analytically continue.
Correct. Yeah.
And that's it. So that's a recipe how we're supposed to do ADS-CFT. And in principle, we could do the same thing here. So I give you a Euclidean circle, and now you have to fill it. Okay?
Yeah.
You can ask how many different ways we can fill it, but let's
Sure.
I'll come to that in a
Sure,
second.
you can do that. Right.
But say you're interested in a black hole type solution, so we know we care about the disk, right? Those are the black hole type geometry. Right?
Sure.
So I give you a Euclidean circle.
No, from the geometry side, there's no problem. If
No,
you-
it's related to this, right? You're talking about the geometry.
I'm
about
just
this.
talking about the SYK model. I'm thinking it started out with the model. The model was defined in Euclidean space.
Yes.
If you were to define in a Lorentzian space, that would mean that in the path integral which defines the model, there will be an e to the is.
I know, but the way we typically do that is we just do everything Euclidean and then we analytically continue at the end. Yes?
Okay, so I'll tell you why that wouldn't work here either. So the first puzzle is that the answers which you get look like they're answers already in a Lorentzian theory.
Before he does anything.
Before I do any analytic continuation.
The answers for what?
Answers for, in this case for example, the bulk propagator. It's a bulk to bulk propagator. Okay, if you were to interpret these coordinates as coordinates of
That's the issue. Okay.
that's the issue, right?
Okay, but
That's the issue I'm addressing, right? Because the whole purpose of this talk is to see to what extent I can take the larger degrees of freedom and convert them into.
Now, we'll come back in a second to identifying this bilocal things. But in principle, if you just look at the normal fields that arise from the bulk,
That's right.
those all behave like in ADS-CFT.
It's nothing different from standard ADS-CFT.
Okay. So this was just a question. So now a point that I want to make is that even from the Euclidean perspective, there's something a bit curious in this example that's not present in other ADS-CFT examples, which is, again, let's just do Euclidean.
There are two boundaries now.
Sorry?
You mean there are two boundaries now?
Well, we could talk about what to do
Yeah.
with the second boundary in a
Yeah.
second. Let's close our eyes, let's not worry
Right.
about the other boundary for a second. But it is true that there are two ways of filling a circle
Okay.
with Euclidean geometries that have SL2 isometries.
Okay.
Well, there's a degenerate case in the middle, but let's focus on this too. So you could fill it with the disk, with the Euclidean disk, and this corresponds to making the isometry of the boundary the non-compact generator of SL2. There's another one, which is the one that corresponds to global ADS2. It has another boundary, so we can worry about that later. If you had a way of capping that geometry, for example, you would not worry about that. There's another way of filling it, and that corresponds to taking the isometry to be the compact isometry of SL2. And in principle, both these saddles are there up to the issue of the other boundary. And then you could ask which one dominates in certain conditions. And then you might ask about how you would do the analytical continuation, right? Because there are different, these are typically continuing in different ways.
Whatever you say is 100% correct. I don't understand the relevance to.
Because whether you get DS2 or ADS2 has to do with how you analytically continue. They're both SL2.
No,
they're both.
The question I'm addressing
I understand.
is very different, actually.
I understand.
Yeah.
That's why we're asking you first. I'm saying that DS2 appears in a different guise in this already from the geometric perspective, which is that both of them are SL2 geometries and just different which is that you're analytically continuing.
Maybe I can shortcut this. Your error is that you are not in control of the analytical continuation. You are not boss of that because in this bilocal theory we started with T and Z. So you could say I could continue T to I tau. But no, you have to continue Z also to I eta. Because that's T1 plus T2 and T1 minus T2. And it all relates to the original time. So you will not be able to continue just one variable.
Yeah, I think
that's a different question.
That's a question whether it's ADS2 or DS2. That's
yes.
Okay. So that's one issue.
That's a different discussion, which is where this kinematical
it's different from that issue.
Yes.
Okay. Okay. So I'll address that question. Before that, let me make this remark, which is actually really intriguing. So you have a theory with an infinite spectrum, an infinite tower of states, and it turns out that this spectrum is in fact exactly reproduced by a three-dimensional model, as a Kaluza-Klein spectrum of a three-dimensional model. So let me describe the version of this three-dimensional model for the simplest case, which is a four-fermion interaction. So what this model is you just consider a single scalar field with a standard kinetic term, so just del phi whole square kinetic term with some mass, and it is living in a metric which is an ADS2 times an interval. And in that interval, you put Dirichlet boundary conditions at the two ends, and the scalar field, in addition being coupled to this geometry, has a potential, and the potential is simply a delta function potential in the middle of this interval. Why this? Because you can solve this model and find that the spectrum is exactly given by an equation which is exactly the equation which appears in the SYK model. Okay. So this is just a few remarks of the standard quantum mechanics. So what you do is that take the three-dimensional field and do a mode decomposition. The part of the modes which are in the T and the Z are the standard ones, and these FKs are the eigenfunctions of this, the operator in the third dimension. So that's a standard Schrodinger problem which you can find in textbooks. And the solution for this is given by that equation, and with a certain choice of parameters, it just becomes this SYK problem.
Sorry, naive question, but in the SYK case, the equation was not the orbital equation with the gammas.
Gammas.
Yeah, with the gamma function.
So that gamma, when q equal to 4, that becomes this.
Oh, that becomes that, okay.
I'll come to those gammas later. Okay, so let me proceed a bit further. So this is exactly what I just said. And calculate the Green's function of this three-dimensional model, namely the propagator of the position space propagator of this model. This is the long expression for this. And once again, you'll end up with this integral over these modes. As I said, these modes come in two classes. One is along purely the imaginary axis, the other is a discrete series. Whenever I write integrals, they are actually one integral over the imaginary axis and a sum over these discrete modes. So you can perform this and get an expression for this propagator. And if you compute this propagator between 2 points which are living on the center of this potential at the delta function, what you find that it exactly reproduces that bilocal propagator which I have written down, which follows from the SYK model. Now that bilocal propagator had some non-trivial factors which comes from the fact that the poles were solutions of a transcendental equation. So those factors are like the residues of those poles, and you might wonder where do those come from, because I now started out with an action which is quite standard kinetic term. They actually come from the values of the wave functions at this point. Okay. Let's proceed further and deal with that special mode and see what happened to that mode in this picture. See, the three-dimensional picture, what was the dilaton in the lower dimension becomes the YY component of the metric, and you can calculate the effect of that on the spectrum by using standard perturbation theory. I will not go over the details of that perturbation theory, and what you find, in fact, it's exactly the form which you can directly calculate in the SYK model. Namely, the 3/2 mode, for example, is corrected by an amount which is proportional to the frequency. And since this parameter A, I said it should be 1/j, this is exactly the form of correction obtained by Mandelstam and Stanford. If we now substitute this into the modified eigenvalue into that expression, what you get is exactly the enhanced propagator of this particular mode. The agreement of this propagator coefficients with wave functions, I think, should have implications on 3-point functions of primary operators of the model. Namely, if I take like 2 fermions and express it as a sum over primaries and descendants of composite operators, so there are those coefficients there, then if you now rewrite the propagator in terms of those coefficients and the 2-point functions of the primary operators which are now normalized, so those coefficients will appear as these factors in this model. So I think, I don't know what the meaning of that is. The fact is that those coefficients can be sort of interpreted as wave functions in the 3rd dimension. I should also mention that this not only works for Q equal to 4, it actually works for all Q. The background is different, it's now conformal to ADS2 cross I. Looks very funny, but at the end of the day, you actually obtain exactly that spectrum with all those gammas. If you ask how did we do it, we did of course a reverse engineering. We knew the spectrum and we guessed that those gammas come if you try to match hypergeometric functions and found a potential which produces this hypergeometric functions. Okay, the meaning of this is not completely clear, but I think it's a curious and possibly non-trivial fact that this happens. And I think when we understand a little bit more about the dual, I think its usefulness will probably emerge. I should make a comment about the large Q limit, which is interesting in this model. This model can be solved in the large Q limit for all values of J. It essentially becomes a Liouville kind of theory. In a Liouville kind of theory, in 2 dimensions, you just see there is just one field, and you might wonder why does that happen. It happens because if you take the original model, it's still true there are an infinite number of modes. However, the residues of the poles of all the modes go to 0 in the Q goes to 0 limit except one of them. And for the comment I made about the 3-point function, what that means is that some of these OPE coefficients, most of them actually go to 0 in the large Q limit, and the only one that survives is the one which is at P equal to 3/2. So it is an example of a model where a mode survives at low energies not because there is a gap in that spectrum between, there is a difference in the spectrum, they are all of the same order, but because of these residues vanishing. It's slightly different from, for example, something what you would find in string theory, where there is actually a scale separate. Here there is also a scale, but it sort of acts in a rather different way. Now let me now come to the question of how do we actually identify the true space-time of this model. We are aiming at a space-time which is Euclidean. And we want to get this from something which came out quite naturally from the model, which happened to be Lorentzian. But before doing, I should say that this 3D language is could be a convenient packaging of the infinite tower of modes, and you should not assume, and we are never saying that it means that there are local interactions in 3 dimensions. In fact, you can see that there are. Now, how did we get a Lorentzian space to begin with? That's because the underlying symmetry is the same, whether it's a Lorentzian or Euclidean. It's always SL2R, SO1, 2 or SO2, 1, the way you think about it. And so we want to ask, how do we get such a space which, from the bilocal space to this Euclidean alias? And I should tell you that in the following discussion, though it is sometimes useful to use the 3-dimensional language, it's not essential to use the 3-dimensional language. You can directly work with the expressions in the SYK. So the issue is the following. So as I said, both the Euclidean and the Lorentzian metrics have exactly the same symmetry. So let me write down the metric on the bilocal space in slightly different, the same thing with different notation. And these isometries are written like this: the dilatation, the momentum, and the boosts, where t is again half t1 plus t2 and eta is again half t1 minus t2. A metric on the Euclidean ADS space is that obtained by flipping a sign out there, whose isometries are given by some standard expressions in terms of the coordinates and their canonically conjugate momenta or delta. And you might wonder if there is a canonical transformation which takes you from one set of generators to another set of generators. Now this is very non-trivial because at the face of it, it's an overdetermined problem. There are just too many conditions to be satisfied if this is to work. But it does work. And this is the canonical transformation. This canonical transformation, if you notice, is a point transformation for the momenta. Namely, the transformations of the momenta do not involve the coordinates. And as a result, it can be implemented as transformations on momentum space fields by some kernel. Rewritten in terms of position space fields, it turns out to be something which is very familiar. It's a Radon transformation. A little bit of remind you what a Radon transformation is in this particular context. Consider a function on the Euclidean upper half plane, which is Euclidean ADS2, if you like, and 2 points which are labeled by T1 and T2, which are on the boundary. What a Radon transformation does is to take this function and evaluate along a geodesic which joins these 2 points and integrate that function over the geodesic with the invariant measure which I written as ds. A well-known property of this transformation is that it intertwines the generators of Euclidean ADS2 and Lorentzian ADS2. For example, the Laplacian of Lorentzian ADS2 acting on the Radon transform of a function is the Radon transform of the Laplacian of Euclidean ADS2 acting on that same function. So this provides a kind of map between Lorentzian ADS2 and Euclidean ADS2.
Sumit, what can
Sure, I'll finish. I should tell you this kind of transform, of course, is known for ages, like probably 100 years. In the physics literature, I think it first appeared in some discussions of the S=1 matrix model by Yonea and Zubicki and many other people. It's similar in spirit to the construction of the Visserian higher spin field, which was done by Dumero et al., which I just mentioned, the way to actually identify the right higher spin fields from the bilocal fields for the three-dimensional ON model, where once again there was a canonical transformation, it was a point transformation for the momenta, and that allows you to write down a transformation. In the context of ADS CFT, it has appeared in other places, in particular in this work which I have just quoted. The use of our use is actually quite different, because we, instead of working on a single time slice as is usually done, we are working on different times, which makes the things quite different. And in fact, as you will see that I think the situation, if we try to use this for say higher dimensional ON theories, this is not probably the right thing, and I think maybe Antal will say a few things about it. In any case, if our guess is correct, then the Radon transform should map the correct eigenfunctions of the Euclidean Laplacian to the eigenfunctions of the SYK kernel which are reduced. Let me just recall the eigenfunctions of the quadratic fluctuation kernel for the SYK model was a particular combination of Bessel functions which was forced upon you by the fact that they should actually commute, the SL2R symmetries should commute with the kernel itself, and those are these particular combinations here. This is precisely what happens, in fact, for the imaginary series. The normalizable eigenfunctions of this Euclidean ADS are given by these kind of modified Bessel functions, and just do that integral which defines the Radon transform. In fact, you precisely recover this particular combination of Bessel functions you have. The discrete series, however, works a little bit differently, and I've just given out what the formula for the discrete series is. So let's put this thing together. One might have thought that this would mean that the inverse Radon transform will in fact transform the SYK propagator to a standard Euclidean propagator. This is almost correct, but not quite. So let me tell you why it is not quite correct. So this is, I rewritten the SYK propagator in terms of the mode sum, and we now need to perform an inverse transform of these functions and obtain in terms of this new variables, and this is the horrible answer which you get. There are parts of this answer which are quite recognizable. These boxes, these products of these modified Bessel functions are exactly those which appear in standard Euclidean propagator in ADS spaces. They are multiplied by some functions which actually has poles, these things, which in this language means there is some redefinition of the fields or external leg factors. In any process, you attach those things. But there is this second class of terms which we don't understand at all, which could be either very interesting or something wrong. I don't know which one it is. It contains, it seems to contain a sum over some different poles, some different contributions which were not there in the SYK structure. This looks a bit weird, but this has happened before. It's a kind of a deja vu from the literature of the C=1 matrix model, where once again, if I can remind you how the C=1 matrix model works out, is that you first rewrite this as a theory of the density of eigenvalues. That's a collective field theory which I and Antal wrote down. But if you really want to relate that to the fields which appear in string theory, in this case we know what the dual is. It's a two-dimensional string theory. Namely, if you want to really match the S matrices of the two theories, you need to multiply the fields by these what are called these leg pole factors, which nobody really, well, there's a sort of partial understanding of it. And furthermore, then what you discover in doing that, and why you do that is sort of partly clear, partly unclear, is that so the two-dimensional string theory has one dynamical degree of freedom, one field theoretic degree of freedom, which is a massless tachyon. But if we actually analyze the string theory itself, namely the RST cohomology of the string theory itself, what you find is an infinite tower of discrete states. These are not really fields, these are the remnants of the higher string modes. So therefore these are not really fields, so they appear as only at particular values of the momentum. So these are like sort of like quantum mechanical degrees of freedom, and this was something completely invisible when you write this as a collective field theory. But as Polchinski and Sumit sort of reformulated that in position space, it became clear that these additional terms, which always appear in the 2-point function of the theory, actually reflect the discrete states. So it sort of led us to a kind of a wild speculation that something, whatever that underlying dual theory is, may have some of those features. We got some very mild indications that this could be true, but I think it's fair to say that we clearly don't understand what's going on here. So far we have dealt with the zero temperature version of the theory. Now at strong coupling, I said there is I'll finish in a few minutes. At strong coupling, there is this reparametrization symmetry which has emerged, and so staying at strong coupling, you could go from zero temperature to finite temperature by using the standard map which takes you an infinite line to a circle. So that's what I did here. And you would have thought that what it does is to take the metric on the bilocal space, which is written in terms of in the light cone coordinates is given here. This is the bilocal space metric, which is the Lorentzian ADS2. You would have thought it would lead to the Lorentzian black hole. And it doesn't. It leads to something else. It's a piece of it's a piece of global coordinates in ADS2. It's a piece because now these variables are all compact with 2 pi, so it gives very funny boundary conditions in that space. On the other hand, if I ask what is the Rindler, ADS2 Rindler or the black hole metric, it is this thing with a sign replaced by sign hyperbolic. So the Euclidean continuation of that ADS Rindler is the Euclidean ADS black hole, which is just a piece taken out, which is given by this metric. And you might ask, does a Radon time transformation actually takes between the correct eigenfunctions between these two metrics? So I've just written down what's the form of the Radon transformation in these coordinates. It's the same space, the upper half plane, in these coordinates. And what you want to do is to apply this to the solutions of what I call FT-SYK, the finite temperature SYK bilocal metric. Now this is a bit tricky to do for finite Q, but at Q equal to infinity, this was solved in the paper of Mandelstam and Stanford, those eigenfunctions. And there are some hypergeometric functions the way I have written here. These are precisely those functions in the zero temperature limit reproduces those combinations of Bessel functions. So this equation is a finite temperature version of the SL2 or Casimir which you solve at zero temperature. On the other hand, if I ask what are the regular eigenfunctions of the Laplacian in Euclidean black hole background in 2 dimensions, you can work them out. The regularity conditions which are given by those. And a test of the usefulness of a Radon transform would be if these correctly transform to those. We couldn't do those integrals analytically, but they can be done numerically, and this is a comparison of the two results. On the left side, we have the Radon transform of these Euclidean eigenfunctions, and the right hand side are the eigenfunctions of this for some values of the parameters which are involved. We have checked it for many values of the parameters, and we're pretty convinced that they are in fact the same. So the thing also works for finite temperature. So let me finish by saying that at least I am very disturbed that the Euclidean propagator has this additional term, and I don't understand where it comes from. Very different from the C equal to 1 matrix model where we knew the dual to begin with. Here we don't know what the dual is. We are trying to find what the dual is. The Radon transform or its analog in the ON model, where it's in spirit exactly the same thing, in fact, is known to reproduce, in the ON model, is known to reproduce the standard bulk boundary map. Namely, I mean, you can have operators of the ON model, the currents, and you can reproduce the correlation functions of the currents by starting with this, with the bilocal theory, and then performing that map, which identifies the right or correct coordinates. From this point of view, its use in reconstructing the bulk space is quite natural. That's something which we are now proceeding to do for the SYK model and see how that works in that case. But it is precisely this procedure which was so essential, which led to these additional terms, and we do not know how to interpret those. So let me finish by saying that we clearly do not understand the story fully, but hopefully we assemble some of the correct ingredients which will help us to discover what is the real dual of this SYK. Thank you.
So, maybe go back to one of the comments that I made. So, say you go back to zero temperature.
Yeah.
Now, in these two pictures, again, you're looking at different generators of SL2. One is a compact generator, the other one is a non-compact generator.
Mm-hmm.
And you say the Radon transform takes you from one eigenfunction of one to eigenfunctions of the other. But one spectrum is discrete and the other one is continuous.
Absolutely.
Right?
That's right.
So how do you see?
So that's the origin of this additional term there, actually. The fact that so one, in fact, written as a Schrodinger problem, one of them has only scattering states, the other scattering states, as well as bound states.
Both spectra are continuous.
Yeah.
Sorry, no.
Both spectra. So just to correct what you said, both spectra are continuous, but one of them also has some bound states.
Let's forget about ABS for a second. Yeah. It's just a fact about the spectrum of SL2 unitary representations.
The Euclidean area spectrum is continuous, and the SYK spectrum is continuous and some bound states.
Well, no, even that if you solve for the eigenfunctions of the Casimir of the SL2R written in terms of what you calling this non-compact thing, this has two sets of solutions, the eigenvalues. One is a continuous series, which is purely imaginary, another is a discrete series.
Yes.
Okay? The continuous maps correctly to the continuous solutions of the Casimir equation for the Euclidean. The discrete series is something which is extra, and that's the part we don't quite understand.
Can we not say Euclidean or not for a second? Let's just take a group, SL2, fix the representation, so let's fix the Casimirs and representation we like, and now we can diagonalize within a given representation the eigenstates of the compact and the non-compact generator. Yes,
you use again wrong words, not compact and non-compact.
It's just these are two generators of SL2. There are three conjugacy classes in SL2.
So both spectra are continuous. Both have scattering states.
Again, let's not use. I'm just making a statement, a very simple statement about representation theory. Take a representation SL2 with a given weight. The generator we call compact is like if you were doing conformal quantum mechanics, it's like H plus K type generator inside SL2,
right.
has discrete spectra. Right, these are the modes of the highest weight.
But typically they would have both.
No, the representations are highest weight states have only discrete states.
But that's not the ones.
But in this case, Sumit has showed you the spectra, so you don't have to say typically.
No, I'm trying to understand what this is.
Typically, you just have to look at the spectra which we had on the board.
No, I know, but the representation theory of SL2 is well known, so I'm trying to understand how this fits there.
Okay, So let me try to put that in terms of the representation. I don't know much about this.
So why even look at books if you already know the spectrum?
Okay, let me.
It's just a moving potential.
So Diego, so we are solving two equations which are the eigenfunction equations of the Casimirs of the SL2R.
Yeah, again, you don't have to tell me about the geometry. They're known, right? The set of eigenfunctions of the SL2 Casimir, they're known, right? You can
Okay,
write them
so
out.
I don't know what is compact or one. In one case, that eigenfunctions admit just the continuous series. In the other case, it has a continuous series and a discrete
Those
series.
are different representations. What you're telling me is that you're mapping different representations to that. That's different from. That's what you're telling me, that you're going to map different representations to each other. That's what you're telling me?
No,
I don't know. These are different.
No, you're going to stay within the same
We would
representation?
never do that.
Okay, good. So if you stay within the same representation, you cannot change these names, right? It's just,
Yeah.
well, you're diagonalizing a different
Sure.
operator inside of SL2. Right, the Casimir is fixed?
No, we would obviously.
Is the Casimir the same on both sides or not?
No, they're not the same.
You just said they were the same.
They are both Casimirs, but I mean, I don't know what you mean by the same. It's like they are both Casimirs.
There's one SL2.
One is written in terms of a certain set of generators, the other written in another set of generators. They are related by a canonical transformation.
Again, there's one SL2 in both cases. What's the Casimir of SL2?
Yeah, I wrote you what the Casimir
Is it the
is.
same on both sides?
What do you mean by the same?
The Casimir
It's
is
not
a-
the same
it's an
differential
invariant.
operator. One of them is an
They are
elliptic
equal,
operator,
yes.
the other is
Yeah,
a...
the same.
Casimirs are equal, sure.
No. What,
So
they're
they're
equal, but one of them is an
simultaneous.
elliptic equation, the other is not.
In other words, afterwards.
But yeah, maybe given that lunch is waiting for us, we can leave the questions for lunch. And are there any other? Okay, can we meet again at 1:30, like in an hour? Or is it okay? And then we'll discuss the program for the rest of the evening.
Should I